Good morning, good afternoon, everyone. Thanks for joining the Cognitive Systems Institute speaker series. Today, I'm happy to introduce Steve Ritter. He's the founder and chief scientist at Carnegie Learning and has been developing and evaluating educational systems for over 20 years. He earned his PhD in cognitive psychology at Carnegie Mellon University and was instrumental in the development and evaluation of cognitive tutors for mathematics. Through leadership of the research department, Dr. Ritter has led many improvements to the use of adaptive learning systems and math education in real-world settings. He's the author of numerous papers on the design, architecture, and evaluation of intelligent tutoring systems. He is lead author of an evaluation judged by the United States Department of Education What Works Clearinghouse as fully meeting their standards, and he's also the lead author of a best paper at the International Conference on Educational Data Mining. Let me welcome Steve Ritter, who will be presenting Using Cognitive Models in Mathematics Instruction. Steve, I'll turn it over to you.
Thanks very much, Diane. As you see on the slide, I'm going to talk about how we use cognitive modeling to improve mathematics instruction. I'm going to start with a quick background on Carnegie Learning, to talk about what we do, then talk about the learning theory that underlies our approach, how we try and understand student thinking, and then some future directions for this work. So Carnegie Learning has been in business for about 18 years now. We started as a research project at Carnegie Mellon University and spun off from work in the psychology and computer science departments there. We publish mathematics instruction in primarily 6 to 12, grades 6 to 12 in the United States. We are across the country, and our primary approach is a blended implementation where students use both textbooks that we produce and the software that we produce, and also teachers receive professional development and support in implementation. The model is typically that a student in one of our classes, instead of using a traditional textbook approach, would use our textbooks, which are more kind of workbook-like. 3 days a week in the classroom, they would be using the software 2 days a week in their regular classroom. And the software is also, of course, available after class for homework and things like that. I'll talk a little bit about the research background and effectiveness studies that we've done as we go on. So we started Carnegie Learning, and like I said, it came out of a psychology department, which was very unusual, particularly at the time, because we felt like the more we could understand about how students think and learn, the better we can help them think and learn. This is the kind of statement that at the time, to me as a cognitive psychology student, seems very obvious, but in fact it's not the way that the education community typically at that time, and even today, most of the community doesn't think about education this way. They think about what schools and teachers need to do. So they think about, if I can explain this topic clearly to students, then I as a teacher have done my job, right? And we think of it from the other way and saying, well, what does the student need to get? What experiences does a student need to have in order to truly understand the mathematics? And when you think of it that way, it changes the way you think about what instruction is about. Our basis, and again from Carnegie Mellon University, was in John Anderson's lab. John's primary research is on a theory and model called ACT-R. If you're not familiar with it, it's a very general model about how people learn, remember, and perform. And what we've done is taken really just kind of a small segment of ACT-R and applied it to instruction. So applied to instruction, the basic elements that we're taking from ACT-R are that complex knowledge, or any kind of complex performance, is composed of simple knowledge components. The knowledge is strengthened through active use, so practice is really important. And then most importantly, that learning happens at this knowledge component level. So what you're really trying to teach students to do is gain and strengthen those knowledge components, as opposed to kind of at the task level of solving a high-level task. But the approach for it is to give students high-level tasks. So we developed software which you'll hear under the name Maffeo or Cognitive Tutor. Maffeo we use for the middle school, Cognitive Tutor we use at the high school level. And it kind of looks like this. We have a sequence of topics, so that picture that you're seeing shows different islands. Each island represents what we call a module. It's a major topic in the course sequence. We give students multi-step problems to solve. So in this problem, the students are given a word problem, and they're going to calculate on what's called the double number line, which is essentially kind of a mapping between two quantities, and answer some questions about that. So we're never asking kind of multiple choice questions and fill in the blank questions. I'll talk about why in a second. And then each step in these complex problems is associated with one or more knowledge components. Those are available to the student and to the teacher in what we call a scalometer, where you see a representation here of a scalometer. So as the student works through a problem, each step in the problem is associated with one or more of these cognitive skills, and the student will see their skill bars going up or down, depending on whether they're doing things correctly or incorrectly, and whether they're able to get it correct without asking for hints, which are available in the system. And then you can see the top bar here is marked as mastered. When the students' bars all reach a certain level, they're all considered mastered. That's when you would be considered to have mastered a particular topic in the curriculum, and then you can move on to the next topic in the curriculum. So the progression through the software is mastery-based, and we use a technique called Bayesian knowledge tracing to estimate the student's level of knowledge on each of these skills, and that's what these bars represent. So what that does is come together in what we call a system of cognitive modeling. The cognitive modeling system is very much like an expert system, and it has two goals. One is model tracing in these kind of complex multi-step problems. There are multiple ways that a student might approach the problem, multiple strategies they might use. And so model tracing is a technique that we use to try and understand what particular strategy the student is using, whether that strategy is a correct strategy or perhaps a known common incorrect strategy, and then what feedback can we give to students about how to progress along that strategy. So if they get lost along the path they've chosen to take, our hints and support will follow them along that path and give them hints and supports that make most sense to the way the student is thinking about the problem. And then there's knowledge tracing, which is a process by which, over time, we're tracking the student's knowledge on those knowledge components. So that is the Bayesian knowledge tracing, and what we use that knowledge tracing for is to select new problems for the students. So we're doing this continuous formative assessment, continually assessing what the student knows at that fine-grained knowledge component level, and then picking problems and activities for the students that emphasize the skills that they need to learn and that build on the skills that they've already mastered. So again, as a review here, we're presenting complex problems to students. Students knowing when to apply knowledge is just as important as having that knowledge. So we want to give kind of mixed experiences where the students need to think about what is the best approach for this, which is why it's a little bit open like that. We try and design tasks to make thinking evident. This is equivalent to teachers saying, show me your work. We allow these multiple solution methods when appropriate, use model tracing to understand what methods students are using, associate these steps with knowledge components, and trace learning on the knowledge components. Okay, so let's dive a little bit into model tracing, just so you understand the value of that kind of technique. This is what you would see from many exams or traditional computer-based instructional systems. You ask a student a question like this: what is 1/2 times 1/5? The student answers, in this case, says 1, which is the wrong answer, I hope you recognize. And that's all the information you have about the student. You might say that this student doesn't know how to multiply fractions. That's all the information that you get. But one of the things that we do when we're developing instruction is ask students to think aloud. So we take these kind of think aloud protocols. I'm going to play one for you. The transcript is here on the screen, but I like to play the audio just so you can hear the timing of how the student says what he's thinking about.
Should I do this one first?
Yeah.
tenths, and 1/5 will go to 2 tenths. Okay. And multiply that, and that would be 1/2.
Okay, so again, I played the audio so you can hear how quick the student says, I have to find a multiple of 10, right? What is that about? It's not quite the correct terminology, but clearly the student decides that he needs to find a common denominator, which of course he doesn't in order to multiply fractions, but still he says he's able to immediately say, well, 10 is a common denominator. And then he also fairly quickly knows equivalent fractions. He says a half is 5/10 and 1/5 would be 2/10. So being able to express fractions in terms of that common denominator is not a problem for the student, right? A bit of a mystery is he says, and multiply that, and that would be 1/2. I think probably some of you are kind of thinking about this, but here's how we think about the process that the student is executing. Says, okay, I need to multiply a fraction. The first thing I do is find common denominators, 5/10 and 2/10. I apply an operator to the numerators. That's what he means by multiply this. I keep my common denominator. I get 10/10. I simplify that fraction, and I get 1. It's, of course, exactly the analogous to the process that you would use for adding or subtracting fractions, but it's incorrect as applied to multiplying fractions. But you can understand how, from the student's perspective, that's a reasonable analogy to make if you don't remember how to multiply fractions. So what's really happening here is, in some sense, a failure of memory. And a phenomenon that we know about psychology is that memory is often a constructive process. It's not just pulling something whole out of your brain, it's reconstructing something. And so if you forget how to multiply fractions and you don't understand why the algorithm for multiplying fractions, multiplying the numerators and multiplying the denominators, makes sense, and you also don't understand why the algorithm for adding fractions makes sense, you've just kind of memorized these kinds of steps, then it's really easy to reconstruct a multiplication algorithm that's analogous to an addition or subtraction algorithm. And that's really what's going on with the student. So what it points out to us is the need to give the student an understanding of where that algorithm comes from. So within Cognitive Tutor, we do have exercises where students are going to be going through the symbolic math, expressing things with common denominators. We will monitor these kinds of activities step by step and give the student feedback. But before we get to that, we build up a conceptual model for students. So this is another activity that students would be doing in Cognitive Tutor. In this case, we're using fraction bars. This happens to be 1/2 plus 1/6. And the idea is the student is able to drag a bar over here, that's 1/2, drags the 1/6 bar, and can see that the sum of those two things is this much. Well, how much is that much? I don't know. I can't actually measure that amount unless I express it as a common denominator, right? If I express them as 6, then I can see, oh, there's 3/6 here, there's 1/6 there. Therefore, I can measure this amount as 4/6. And of course, I add the numerators, I add the 3 and the 1, but they're 6ths. I wouldn't add the denominators, right? We're trying to give students an intuitive understanding, and then we're also connecting that understanding to the formal algorithm, right? Here's the numerator, keep the denominator the same, add the numerators, keep the denominator the same. In contrast, the conceptual model that we give for multiplication is an area model. So here the student is given 2 number lines, a vertical and horizontal number line. The student has, and again, this is a partially completed problem, so the student has done part of the work already. The student has said, okay, let's divide this number line into fifths. Here's 1/5 shaded. The vertical number line is divided into halves. Here's 1/2 shaded. The overlapping area is obviously 1/2 of 1/5. Well, how much is that? Well, just from the diagram, you can read it off and say, well, I have 10 equal parts. One of those 10 parts is shaded, so it must be 1/10. But you can also read this as an area model. Well, that's 1/2 times 1/5, which is going to give me the shaded area of 1/10. So again, the idea is not so much that students are going to draw a diagram like this when they need to multiply fractions, but we're giving them the conceptual understanding that acts as the basis for memory, for understanding how to reconstruct, if they forget the specific steps, how to reconstruct and think about the process that they need to do to execute that. knowledge tracing. So let's talk about how we think about what these knowledge components are and how we monitor them over time. So this is another type of problem within Cognitive Tutor. This would be kind of 8th grade linear algebra problem. We give a student a word problem. In this case, you're flying an airplane that's traveling at 325 miles an hour. And the student's task is to construct a table that represents this relationship as well as answers these questions like how far we've flown in 2 hours, how many hours are required to go 325 miles. This red circle represents the data or the step in the problem that I'm going to talk about. The student needs to fill in the quantity names, units of measure, answer all these questions. So basically fill out the spreadsheet. But I'm going to focus on students' work in this particularly important step, which is saying what's an expression for the length of the flight given the time. So the correct answer would be something like 325x. And the form in the tutor is students will get a problem like this. They will answer it, and then if they haven't mastered their skills, they'll get another problem that's similar, not the exact same type of problem, but it's a similar problem. And really what the skills are doing is the skills are a model of what we consider similar in terms of the student's understanding. So here's some data from about 5,000 students doing problems within this type of problem. So this is not data about that specific airplane problem, but it's data about linear algebra problems in that form. And this is specifically about writing that expression within the cell. And what we would expect to see would be to follow kind of a parallel of learning, which means over time, and in this case we're kind of measuring time as number of problems completed, because in each problem they have that step of writing the expression. And then we're looking at percent correct here. So we would expect improvement in percent correct, and fortunately we do see improvement in percent correct over time across this group of students. But there's kind of a strange pattern here in that the initial performance is about 26% correct on the first problem that students see. So in other words, 26% of students are able to get it right the first time we give them a problem. They've already learned this skill somewhere else. The second problem that students receive, they do really the same, very slightly worse. Then the third problem, there's a big leap, and then from there they go up. So why isn't the learning fairly smooth across students? Why is there this kind of plateau and then a leap? And when we see this kind of pattern, we know that there may be a problem in the representation of what these knowledge components are. And so what I'm showing here is this is the curve, the exact same graph that you saw before. And what I've done is within that data set, I've separated out problems that have a positive slope. So these are problems which is, y equals ax, where a is a positive number, so the numbers are increasing, versus a negative slope. And you see within the positive slope class of problems, so this is the first positive slope problem, second positive slope problem, third positive slope problem, and this is the first negative slope problem, second negative slope problem. But the problems are intermixed. So the second positive slope problem might be the third problem in the section that the student sees. And that's the explanation for these results. If the first problem is a positive slope problem and the second problem is a negative slope problem, there's no improvement. What that tells me is there's actually no transfer between knowing how to do a positive slope problem and knowing how to do a negative slope problem. Why is there a leap in the third problem? Well, the third problem tends to be either a repeat of a positive slope problem or a repeat of a negative slope problem. And so there is transfer from positive slope problems to positive slope problems and from negative slope problems to negative slope problems. Because we know that there's that transfer there, we know that representing the difference between positive slope and negative slope is a knowledge component. It's something that we need to monitor students' ability to do. And this is an improvement that we actually can make to the system based on this data. We've made a new discovery about the way students think about solving problems. Mathematically, it shouldn't matter, but it does matter. And so now we monitor student skill on being able to do a positive slope problem and a negative slope problem separately. Through the process of developing this, we've been, again, from our research background, been very careful to evaluate our effectiveness in real classrooms. This is one of the most recent and probably the largest, most rigorous study of an algebra curriculum ever done. Was done by the RAND Corporation, random assignment study in 147 schools, over 19,000 students. The results showed in the second year of implementation by schools, nearly doubling in student growth of knowledge. This was a study where implementations varied quite a bit. When we look at students who use the software for a significant amount of time, this actually amounts to about a quarter of what we'd like to see students using the software, but even with that minimal use, we even see even stronger results from students. I'll talk very quickly about some of the future directions that we're moving in. One is, as I talked about with that knowledge tracing, we're using student data to refine skill models so that understanding what are the underlying difficulty factors or knowledge components that students encounter when solving problems, which is basically a question about what makes problems similar or different. We're building an automated system to try and test hypotheses about what's the best model. Part of that modeling is also fitting our Bayesian knowledge tracing parameters. So we have parameters that estimate what's the probability students already know the skill, how quickly do they learn that skill, and how do we model that over time. And then also we're using a lot of data-driven task design, so we can look at specifically the kinds of errors students are making and how do we improve the task design such that students don't make those errors and transfer better to other tasks. A big factor in this is implementation. I don't want you to get the idea that the software works on its own. The teacher has a really important role to play in the classroom and in scaffolding the student's use of the software. On the left here is a graph where we've shown that across classes, some teachers, although the software is designed to implement mastery learning, teachers are used to pacing the students at the teacher's own pace and saying, okay, we're moving on, we're going to do quadratic equations today, everybody move on. Some teachers do use the software that way, placing students where they think the class should be as opposed to what the student is able to learn. What we see when teachers violate mastery learning is that error rates go up over time. So as the school year goes on and on, the students are missing more prerequisites, get more confused, start to make more errors. Also, this is from the RAND study. We see at a school level, there's an implementation dip. So when they first encounter this curriculum, which involves a different method of teaching, there's an adjustment period that's needed. So the improvement that I'm talking about actually happens in the second year of implementation by the school. This doesn't have to do with student familiarity or even teacher familiarity. It's really about the school understanding how to fit the instructional approach into their overall academic plan. And then finally, one area that we're looking at very closely is assessment. So we use continuous formative assessment to pick activities for students. We're starting to take seriously the idea that this continuous formative assessment provides a better method for doing what's called summative assessment, for deciding at the end how well did the student do in the course, did the student pass, what should the student's grade be, those kind of roles of summative assessment. And so we build a metric which we call applause, which sums up these formative assessments over time to produce a summative assessment. And we're really actually hoping to work with states to replace the kind of high-stakes testing that goes on today with kind of continuous formative assessment testing, which we think has a number of big advantages. And so that's it. So I think we have about 5 minutes for questions.
Thank you, Steve. Let me just ask the audience to please press *1 to unmute your phone line, or press the microphone button on your computer if you're using the computer, but *1 to ask a question. That was fantastic, Steve.
Yeah, hi, Steve. This is Jim Sporer. Good to reconnect after many years.
Hey,
thanks.
Jim.
Yeah, so Steve, what other domains is this being applied to besides mathematics?
Yeah. So in Carnegie Learning, when we started, we thought we would rapidly move beyond math, but it turns out there's a lot to do in math. So we've only done this in mathematics, but historically, and various research projects have applied this to computer programming very successfully, various areas in science, and even things like historical reasoning, constructing reasoning graphs, and some language skills. So I think the general applicability is to areas where there's at least a component of problem solving, where you can think about particular methods and paths to a solution, and where scaffolding along those paths is a valuable kind of feedback to get.
Mm-hmm. And if Steve, if you were going to scale this up to those other domains, and you had all the resources in the world to do it, how long do you think it would take to scale up to other domains and get kind of...
Typically we think of a full-year course. So our approach has been to build a full-year course, including the text and the software. At that level of commitment, it usually takes us about a year with a team of 5 or 6 experienced people to kind of build out that curriculum. So it's about that level of effort if you think of it as a kind of K-12 school year. There are other models where if you were doing kind of a supplemental, less, you would need to cover less. That might be even quicker.
Okay, and then to get the empirical validation and iterate a few times, in your experience, where do you kind of hit the sweet spot? Do you have to do this like 3 years, 5 years, 10 years to hit a sweet spot, or do you pretty rapidly converge on, an empirically validated optimal kind of level?
Yeah, that's a really good question. So that RAND study, which is kind of the gold standard type study, the good thing is it's a gold standard study. It gives you makes you able to make causal conclusions that the improvement in the students was really caused by the software because of random assignment and things like that. But that study was very expensive to do. It took 7 years between when we applied and when the results get published. It's tremendously slow, and so what we and others are working on are ways to get not quite gold standard data, but better evidence of effectiveness in a much shorter time cycle. So some of the things that we're doing to kind of automate cognitive model improvements, we're able to kind of do on the fly, right? We can put out a new version of software, measure within the software if that's improving student outcomes, reducing error rate, reducing the number of problems that students need to do to reach mastery. And we can take that as initial validation of the improvements that we've rolled out.
Yeah, this is terrific. Thanks so much, Steve. Any other questions or comments?
Yes. This is Martin Apple. Question has to do with, can you construct a parallel expert system that would begin to assist even more what you're doing?
Right. So we do think of the system that we've constructed as a kind of expert system. It differs from a lot of expert systems in the sense that it's not necessarily looking for the most efficient solution method. It's trying to represent multiple solution methods, and that's the basis of that model tracing technique, right? Is that if we can represent multiple solution methods, we can identify which of those solution methods students are following. One of the interesting things that we're thinking about as well is constructing an expert system to model the instructional component of this. So we're modeling the student, but we haven't gone down the path yet of modeling the teacher's interaction. And so one of the things we're thinking a lot about is, how do we think about this more as a dialogue and modeling the teacher end of things?
Thank you for the questions, and we are at the top of the hour, so I'm going to ask for further discussion that you continue asking questions of Steve in the LinkedIn discussion group. I will post something really shortly about that. And Steve, this is a fascinating work, wonderful work that you're doing, and thank you for being our presenter today. Audience, thank you for joining, and we'll see you next week.
Thanks very much.
Bye, everyone.